FPGA-based control of an extendable bidirectional DC-DC converter for EV application. So the main objective was to design a bidirectional DC-DC converter for 800-volt architecture. The circuit diagram of the proposed end-stage EBDC is shown, with the fundamental stage comprising of two inductors, four switches and two capacitors, followed by the second stage comprising of a single inductor, two switches and one capacitor, and it can be extended up to n stages. The corresponding voltage equations for both modes of operation is given here. The highlights of the proposed converter is also given, where there are two switching strategies that has been incorporated to the proposed converter. One is the synchronous switching strategy, where the operating switches are turned on and off simultaneously. The other one is the phase shifted switching, where the operational switches are given a phase shift of 180 degrees between each other. So coming to the synchronous switching operation in the step up mode, the switches S1 and S2 are the operational switches. The corresponding equivalent circuit for state 1 is shown here, where the switches S1 and S2 are turned on simultaneously. Similarly, for state 2, both switches are turned off simultaneously with the equivalent circuit shown. The experimental setup and its waveforms can be seen. Now coming to synchronous switching operation in the step down mode of operation. Here the operating switches are switches S3 and S4. Here also it is divided into two switching states given by state 3 and state 4. The equivalent circuit of state 3 when switches S3 and S4 are turned on are given here. Similarly, in state 4 both switches are turned off. Now coming to phase shifted switching operation, the analytical waveform shows that the operating switches S1 and S2 are turned on with a phase shift of 180 degrees. So it has three equivalent circuits given by state 1 where switches S1 and S2 are turned on, and in state 5 S1 is on and S2 is off. For state 6 S1 is off and S2 is on. For the closed loop control of EBDC, the block diagram is as shown, where the PI controllers are implemented in the FPGA platform, with the pulses given to S1 and S2 for the step up mode and to S3 and S4 for the step down mode of operation. Here the responses are plotted for the disturbances in input voltage as well as the load current. Here the waveform shows that the output voltage is effectively regulated at 800 volt for the change in input voltage and also for the change in load current as shown. Similarly, for the step down mode of operation, it is regulated at 80 volt for the change in input voltage as well as for the load current.